All right, PHYS 210 students, listen up. Today, we are digging into the absolute bedrock of mechanics, Newton's 3 laws of motion. You can think of these laws as the official rule book that connects forces to the motion we see all around us. Seriously, if you can master these, you've got the key to solving pretty much any problem this course will throw at you. So, let's dive in. First, we're going to start with the language of mechanics itself by figuring out what a force actually is. Then, we'll walk through each of Newton's 3 laws one by one: the law of inertia, the legendary F equals ma, and the action-reaction law. And to wrap it all up, we'll see how these laws come together to form your essential mechanics toolkit for the rest of PHYS 210. So before we can even get to the rules of motion, we have to understand the main character in this whole story: force. It is the fundamental concept, the thing that drives everything we're about to study in classical mechanics. At its heart, a force is super simple. It's just a push or a pull. But here's the most important idea, so don't miss it. A force isn't something an object has. No, it's a measure of the interaction between two different objects. You got that? No interaction, no force. Period. Okay, and this is absolutely critical. Force is a vector. That means it has both a strength, a magnitude, and a direction. And why does that matter so much? Because when you have a bunch of forces acting on something, you can't just add up the numbers. You have to find the vector sum, which we call the net force. And we measure it all in a unit called the Newton. So what in the world is 1 Newton? Well, it's the exact amount of force you need to take a 1 kilogram mass and get it to accelerate at a rate of 1 meter per second squared. This definition is beautiful because it perfectly links the 3 key players in mechanics: force, mass, and acceleration, which, perfectly sets us up for the laws themselves. All right, on to our first rule, Newton's first law. I like to think of this as the default setting for the entire universe. It basically tells us what objects do when you just leave them alone. This is the law of inertia. And in plain English, it just means objects are kind of lazy. They just keep doing whatever they're already doing. If an object is sitting still, it's going to stay still. If it's moving, it's going to keep moving in a perfectly straight line at a constant speed unless some net external force comes along and messes things up. Now, this do-nothing state leads us to a massively important concept for solving problems: equilibrium. An object is in equilibrium when all the vector forces acting on it completely cancel each other out. To put it simply, if the net force is 0, then the acceleration has to be 0. And you really need to pay attention here, because this is a super common mistake. Equilibrium does not just mean not moving. Sure, an object sitting perfectly still on a table is in equilibrium, but a car driving on a straight highway at a constant 100 kilometers per hour, that's also in equilibrium because its velocity isn't changing. Both of those states have 0 acceleration. Okay, so the first law tells us what happens when forces are perfectly balanced. But what happens when they're unbalanced? Well, that's where Newton's second law comes in. This is the big one. The moment physics went from just describing motion to actually explaining what causes it. So the law gives us this really precise relationship. If you push harder, you increase the net force, you're going to get more acceleration. Makes sense, right? But if the object is heavier, if it has more mass, you get less acceleration for that exact same push. Mass, in this context, is really just a measure of an object's resistance to a change in its motion. And all of that boils down to this one master equation: net force equals mass times acceleration. Seriously, tattoo this on your brain. It is the quantitative link you will use to solve the huge majority of problems in this course, connecting the cause, the force, to the effect, the acceleration. Now, knowing the equation is the easy part. Applying it systematically, that's the real key to success. This 4-step process right here is your recipe for every single problem. Don't skip a step. I mean it. This process turns even the most complex situations into something you can actually manage. And this table? This is your guide for step 3, resolving forces into components. Just look at tension, for example. If you have a rope pulling at some angle theta, you can't just plug the full force T into your x or y equations. No way. You have to break it down into its components: T cosine theta for the x-axis and T sine theta for the y-axis. You're going to do this for any force that isn't perfectly horizontal or vertical. And here's a direct connection back to your kinematics work. If a problem doesn't give you the acceleration, but instead gives you the object's position as a function of time, x of t, you know what to do. You find the acceleration by taking the second derivative with respect to time. Once you have that value for A, you can plug it right back into F equals ma to find the net force. See? It all connects. All right, let's get to our final rule of the game, Newton's third law. This one is all about symmetry. It tells us that forces never, ever show up alone. Every single force in the universe has a partner. You've heard it a million times. For every action, there is an equal and opposite reaction. But the real insight here is that a single isolated force simply cannot exist. It's impossible. So whenever you identify a force, you should always be able to point to its counterpart, the other half of that interaction. Here's a kind of mind-bending example to make this real. The Earth exerts a gravitational force on you, right? We call that your weight. Well, at that exact same moment, you are pulling up on the entire planet Earth with a force that is the exact same magnitude. Wild, huh? Mathematically, the third law is just beautifully concise. The force that object 1 exerts on object 2 is simply the exact negative of the force that object 2 exerts back on object 1. Same size, opposite sign. That's it. So, let's put this all together. These 3 laws aren't just some abstract ideas from a textbook. They form a powerful, practical toolkit that you are going to use to analyze and solve problems for the rest of PHYS 210. Look, everything we've just talked about really boils down to these 3 practical skills. If you can draw the forces correctly on a free body diagram, apply the second law in its x and y component form, and spot when things are in equilibrium, you've basically mastered this chapter. And why does mastering this matter right now? Because these laws are the direct prerequisite for everything that's coming next. You're going to use them to analyze friction, and you're going to have to adapt them to solve problems with uniform circular motion, where the net force is always pointing toward the center of a circle. Bottom line, these 3 laws are the foundation for everything you're going to do in mechanics. Master them now, get comfortable with them, and you will be ready for anything this course throws at you. Newton's laws are incredibly powerful. I mean, they describe the motion of almost everything we can see, from a thrown ball to a planet orbiting the sun, but they aren't the complete story. So the final question I'll leave you with is this. At what scale, either very, very large or very, very small, do these elegant classical rules start to fail, requiring a whole new set of rules to describe how the universe really works?